I guess.
Yeah.
Can I?
Yeah.
Okay. Everyone, let me introduce to you Kam. I think that you already know him. He's a postdoc in our group, and he's quite an expert on various things and quite a world traveler. Been in Australia, in USA, I guess, in Germany, in Italy. So a long history. And today we talk about quantum. Point number one, quantum kernel.
Okay. So I split my talk into 4 movements, okay, and we'll try to give you some overview of the whole things, okay, the quantum machine learning, but not the whole one, okay, it's still limited, okay, and I will first present this major method called the quantum kernel method, okay, and okay, the big idea is that all the machine learning, the quantum machine learning has a very serious issue, is that everyone knows work in this field is called the boundary factor. Okay, so if you try to tune the parameters, but if the parameters get more and more, then finally you realize that the classical gradient descent method failed completely because your parameters regime is now geometrically it's like a plateau, okay, and you know where to go. Okay, so in the gradient family is potentially is the order of 1 over a constant, okay, a power of n, okay. So it increase very quickly exponentially with the size of the system, okay, and then, but in another way you can do this so-called the convex optimization. And in that case, you can have a very pure deterministic solution. In that case, it also is sharply hard. Okay, usually you cannot scale up with. Okay, so it's a dilemma. Okay, how to move forward. Okay, so sorry. So there's other ways to do this. Okay, so each method has pros and cons, and here the best thing for this quantum kernel method is that it don't change the parameters at all. It's a non-variational method. Okay, so you just do this type of picture maps. Okay, so you have some classical data, whatever data that's the input from the might be the biology, might be from the industry. Okay, it's totally classical data. You find some way, okay, pretend you know how to do this, okay, but usually you don't, yeah. But in case you do some way, okay, to do it, then you do the picture map, okay, then the data is encoded in the wave function, okay. So in the high dimensional Hilbert space, and then with that, you can evaluate the similarities of the data that's called the kernel matrix, okay? And the good thing is that when you map to higher dimensional Hilbert space, so the data, okay, you see many times this kind of picture, okay, so in the 2D, okay, something is hard to separate, they might mix together, but when you project to high dimensional, okay, you can easily separate them, okay, then you know which one is good, which one is bad. And also with that method, you totally avoid this kind of vanishing gradient issues. Okay, and mathematically, how to do this? Okay, so in a one line, one sentence is that you have the picture embedding. Okay, so you have your state. Okay, in the high dimensional Hilbert space. And then you compare all the overlap. Okay, so you have a matrix. Okay, a matrix. Okay, that is the similarity of the data. Okay, in the quantum space. Okay, and you can do it in many ways in the hardware. Okay, this is a very technical things. Okay, and this called the fidelity in quantum kernels because you're evaluating the quantum similarities. Okay. But it has each thing has an advantage and disadvantage. Okay, so in the following slide, you look at this method also has some disadvantage for the exponential concentration. Okay, so there's another way to do this. Okay, It's called the projective quantum kernels. Okay, in that case, you don't compute, okay, the wave function itself. You first of all you compute the boundary. Okay, so you compute the reduced density matrix. Okay, here rho is one body reduced density matrix. Okay, now you have many one body reduced density matrix. Then you compute the distance. Here f means the fidelity distance. You can have many ways to do this. This is just a example. Okay, and gamma is the parameters. Okay, for you to enlarge and then shorten the distance on the high dimensional Higgs space. And
what do you mean for reduce? Reduce with respect to what?
Your system, for example, you have you map to some physical system. Okay, for example, depends on your problem. Okay, it might be a 1D spin chain or it might be a 2D spin system. Okay, here just for example, if for example if it's a 1D spin chain, okay, then you might take it might be the first two as the the first one is in the system, then the others are the environment. You trace it out, okay. Then you do the same for the second, the third, okay, and oops, disappear. That's my computer problem. I see. Okay, wait a moment.
So while we wait, can I ask you what do you mean by extreme expressivity there?
Okay, that one I will talk about. That's very important. Okay, that is related to the shortage of this method. Okay, and then immediately next line I will talk about.
And then before that one, actually, why, like, how you in the right column, how do you compute those norms of differences? Actually, F means what here? Fidelity or?
Yes. You have the distance, okay, the square root, okay, of the density matrix. Yeah, then inside, for example, you have rho, and then you have the square root of sigma, circle of sigma. Okay, you see it in the FD textbook of the.
No, sorry. Which norm is that? I'm asking.
It's the fidelity norm. You can use other norm. You can use as k distance. Okay, yeah. Just for example, yeah.
And one QEC tomography, why? What do you mean algorithm evaluation of QEC?
You do experiment, okay? You read out all the 1D reduced density matrix, and then it's experimentally, technically, how to do this kind of, because it's just mathematical expression, okay? So experimentally, how to do, you rely on this 1 qubit state tomography or other more complicated methods.
Meaning that each state, you do tomography on each individual state?
Yes.
We should do a qubit, or we should do.
No, and why 20 qubits then? I don't really. Why does that require 20 qubits? I'm not wondering.
You now try to encode your information in your physical system. Okay, so this one is more straightforward. Okay, but it has some disadvantage. So you do another kind of mapping. Okay, this is another kind of mapping.
Yeah, and why 20 qubits? I mean.
Just one typical way to do that. Okay, the other way. Okay, I move a little bit forward. Sorry. Okay, so and here if you want quantum advantage, you need to conquer some difficulty. Okay, so your data must have your quantum kernel must induce some very different geometry than the classical kernel. Otherwise, you will see later that it can be dequantized. Okay, and also your problem cannot be deal with the classical models. Otherwise, no reason to introduce the quantum model. And also, so it's a very strict requirement. Also, your problem also need to align with your data align with the quantum model. Okay, so in this way, the classical models does not work and the quantum model works. Okay, so this in words. Okay, what's the provable quantum advantage? Okay, but this is the core picture, the core idea that you can take home is that each method has its challenge, and the challenge for the quantum kernel method is that, for example, here it's just a cartoon, okay, for you to have an idea. So you have the matrix, okay, the quantum kernel matrix, okay. In that case, you have large value on the diagonal line and some minus values, some small value on the off diagonal lines. That's okay, okay. But when the size goes large, okay, might be 1,000, 3,000, then all the feature loss, okay, because you only have the diagonal elements, okay, remaining, okay, and each element is opposed to one of another diagonal element gone. Okay, it's very similar to equivalence. Okay, so you cannot has a quantum kernel with the size too huge. Okay, it's always there. This problem called the exponential concentration, always there. Okay, and so this is 4 horsemen. Okay, of the exponential concentration. Okay. If your quantum circuit, okay, too complicated, okay, and in the terminology, it's called the expressivity, okay. Now, if you have very complicated quantum circuit, okay, usually fail, okay. If you compute the quantum kernel, you end up with the diagonal line. And if your quantum circuit involves a very complicated entanglement, falling law entanglement, okay, then also failed, okay. You will end up with the diagonal line. And if you also the global measurements means that, okay, also you say it's similar to the falling law entanglement, okay, if you cross the data spread the whole quantum space, then you also end up with the diagonal line. And finally, there's always there the noise, okay, and if you cannot improve the noise, okay, what all the computation is meaningless, and you end up with a diagonal line.
Well, sorry, why global measurements should be a problem here as opposed to not global ones? Like in principle, you expect that if you measure more of the states, you distinguish more easily different states, right?
I will also explain it immediately. So you have your data, classical data, you map into the high dimensional Hilbert space, right? But you need to very precisely, okay, for this mapping, okay, if for all these high depth circuit, okay, falling law entanglement or global measurement, you can mapping the data to a very uniformly distribution and nearly similar to the random data on the high dimensional space. Okay, so we cannot capture the geometry of the original data.
But that's about, like, I understand that for expressivity and entanglement, let's say, but because those are about how you encode the information, right? But the measurement is not related to how you encode it, or is it? Unless you
Okay, it depends. This is, I guess here the meaning is that on the circuit, okay, some method they use the measurement a seed, okay, algorithm, okay. Then in that case, if you have the global measurement, then it will have the similar issue.
So, sorry, what kind of seed you said? I didn't understand.
What I said is that just like the entanglement, the measurement you can do in the local part of your circuit. But if you defect all the circuit elements, then it's worse.
Yeah, but that's what I'm saying. Now, usually, if you measure all parts of the system simultaneously, it's easier to distinguish different states. Right? Less of it.
Okay, we can discuss it later. Okay, I think we can discuss it.
Because there are with the number of possible measurements, we have to go into the scales.
Okay, yeah, I don't know if this is optimizing your measurements or not. That might. If you have to optimize over measurements, I guess yes, I don't understand.
Okay, sorry. Okay, and then, okay, so that's the, okay, sorry for repeating. Okay, so it's a take-home message. Okay, so your it's a paradox. Okay, if your quantum circuit too simple, okay, then you can't capture the data pattern. Okay, so you fall into the left. Okay, but if your quantum circuit too complicated, okay, then you end up with some points. Okay, random light. Okay, they're all orthogonal in the high dimensional space. Okay, so it's in the right side. Okay, so it means that you need to very problem orientated, okay, to choose your quantum circuit. You cannot be too short, you cannot be too long. Another issue is that another disadvantage of this method is that it's under the threat of dequantization. Okay, so this is a very strange word, but all the community use this word. Okay, so if you already has a quantized version, okay, of the data, but somehow, if you cannot prove it really better than any classical computer algorithms, then someone will pop up and then find out a very efficient classical simulation. That's called the quantization. Okay, and it started from the 2019, and many algorithms are dequantized, okay, by some clever choice. For example, here, if you're for 1D circuit, okay, so people can use this kind of metric product state, okay, so it's a fully dequantized, okay, and the classical metric product state can simulate this area law 1D circuit in the polynomial time, okay, in the order of n chi power of 3, okay, so chi is called the bound dimension, okay, and a zero quantum advantage is there. So 1D is basically already beaten, okay, but for the 2D, people can somehow introduce this kind of entangled pair state, okay, but for this case, there's some theory, okay, say that okay, the exact classical simulation is sharply hard, okay, means very hard, okay, harder than the NT. But okay, if your circuit it just has the area law, okay, entanglement, then there is some approximate, okay, simulation, okay. It's not exact simulation, it's approximate simulation. And this kind of approximate simulation, okay, rapidly narrowing this gap. Okay, so it's a competition, okay, you never know, okay, if you have no theoretical proof that some days later, maybe a few years, and you'll be dequantized. Okay, so you can tune, okay, a parameter, okay, called a bandwidth parameter, okay, to control how your point scatter on the high dimensional Hilbert space, and there's always a price rate. If your data scatter too evenly, then it's just look like random points on the sphere. Okay, then it's useless. If it's too concentrated on a local area, then it's okay. You can use it to predict something. But in that case, it can be quantized. It look like will be very similar to some classical kernel. Okay, and so you need to very smartly, okay, to choose your method of embedding. So it's just cartoon. Okay, so the empirically, okay, you need to learn, okay, it's not automatically, okay, you need to find a way to embed the practical data, and also you need to consider the constraint, okay, in each physical system, superconducting trap ion or the photonics platforms, they all has their unique noise issues, and so that's just a cartoon. Okay, tell you that each problem, okay, you need a unique picture map. Okay, and how to do it. Okay, currently still under active research. For example, one thing is known is that you can use one generic embedding, okay, for all problems, okay, not hopeless, and also too complicated quantum circuit is hopeless, and then the falling law entanglement is also hopeless. And potentially, okay, this part is something people don't know, okay? You might use the theory in symmetries, okay, may help. You might use the theory in group structure, for example, the protein problems, they actually have the rotational symmetry, okay? And then to help you to restrict the depth of your circuit. And then you use a simple design, not simple, not too complicated design, okay? Then it might bring some provable advantage. That's also something I will talk about later. Okay, so okay, that's just works. Okay, so before I moving on, so you have any questions about just a big picture? Okay, the quantum kernel methods advantage and disadvantage. Okay, then I'm going on. Okay, a little bit more specific. Okay, talk about for one of the routines. So you still remember then there's many routines. Okay, some some are the superconducting platform, some are the trap-out platform, and this one is the most doable. Okay, someone in that paper, Nature Photonics, they already experimentally performed. Okay, so this is doable. Okay. And for on the photonic platform, and the reason is that and the classical machine learning method is very energy consuming. Okay, so it cannot grow forever. Okay, certain quantum it must pass through the quantum method, and this already explained. Okay, so cannot go too high dimensional. Okay, if too high dimensional, you will see something like that. Okay, everything is orthogonal here. You just have a state. Okay, everything is a random line. Okay, this something. Okay, I want to talk is that in that experiment. Okay, they have just a 6-mode, okay, very simple on the table. Okay, you have a glass strip, okay, 6-mode, it's just a cartoon, okay. Then you inject, okay, specific, okay, 2 boson Fock state, okay. You do in the experiment ethically, and then without the sampling of the output probability, they can separate which one is bad, which one is good. They have get the correct label of the data, but it's very small. Okay, so two photons and 6 mode, and it's basically the Hilbert space dimension is 21. Okay, but it's already done experimentally. Okay, and okay, these are already explained, I guess. Okay, so the only is that how to do the embedding. Okay, for example, the phase shift is easier to get. Okay, if you have the classical data, okay, this one to extend, then you can shift the angle, okay, to high xi. Okay, then you do the phase shifter, but phase shifter is not enough. Okay, then you might be the brim splitter, the force the mode to crosstalk, and that is a little bit technical, complicated. Okay, so you can go back to read the paper. But the picture is always like this. Okay, so you have a source, some laser source. Okay, so you just input, then you do the phase shifter, beam splitter is always experimentally doable and scalable. Okay, up to a few hundred of the mode, and also high fidelity. Okay, so this platform is really doable. Okay, then you do the detection. And you can distinguish 2 things. Okay, one is that when you send the light through the circuit, okay, you let them crosstalk, let them have the quantum interference. Then this type of kernel will result in the distribution of the probabilities a metric permanent. Okay, so this is very hard to compute quantity. Okay, already theoretical proof that okay the exact simulation of this quantity is extremely hard, and a benchmark for comparison is that if you send a line, okay, with a time delay, okay, they have no correlation, then these are distinguishable bosons. Okay, And then they are classical particle behavior, and they have no interference. So in that case, they are still metric permanent, but they are without the interference. So it's a permanent of the modular square. Okay, this one is a permanent, okay, modular square.
Sorry, can I ask you? So here you mean the modular square of permanent is the kernel here?
This thing, you have the output of the probability, so you scatter your particles through the modes. Okay, so originally you have 1, 1, 0, 0, 0, 0. Okay, after the crosstalk, okay, with the spring splitter, then you see another distribution. It might be 0, 1, 0, 1, 0, 0, something like that. Okay, then you can compute the output probability. Then it can be expressed in terms of the permanent. Okay, it's quite standard. Okay, it's called the boson sample.
No, yeah, that probably is distribution, I know that, but I'm asking the kernel matrix. So are you saying the permanent is the kernel matrix or something else? I'm confused. Like, what is the kernel used there?
This was still the fidelity kernel. Yeah, I forgot to put that. It's still the fidelity kernel. So you have the picture map to the wave function, then you compute the fidelity. There's an overlap. Okay, so you still have the fidelity kernel in this case, and then you can show that already proved in the paper that it is related to this boson sampling problem.
So the elements, so the fidelity with the different training states essentially.
Yes. No training. You just embed your classical data into a quantum state and then compute their overlap. That's it.
Between the states.
Yes.
And so to compute the overlap between the training states, like you relate that quantity to the output probability distribution through the permanence. That's what you're saying.
Yes, the output probability is determined.
The output probability is determined by the permanence.
Not determined, permanent, sorry.
And that's related to the quantum kernels, you see. Because otherwise you have to do a swap test or something. Here they don't do that. But usually to compute the kernel elements, you have to do a control swap test. That's the standard way. Here, do they do something like this, like this, or something else? That's the question, I guess. How is the kernel matrix actually measured, if they are measuring it? Unless I'm understood that, I don't know.
I guess that the permanent is the kernel.
Permanent is
Yes. You have the data is embedded in the gate of the circuits, and so it's just problem of determining the probability to start from some configuration of order to the same thing.
So the information is inside the view, essentially there.
SLT should be that.
Okay, let's see the data.
Okay, thank you. Okay, so now it's clear. Okay, and then, I already mentioned the shortage of this method, so you cannot choose arbitrary problems. Okay, you can only focus on some very specific subject. Okay, that the classical computer is the weakest. In that paper, it's a design object. They generate a research cartoon. Okay, they generate some random data with no label, and then they compute a geometric distance. Okay, I don't give the definition here. And then they prove that there's the existence of certain label that will make the quantum kernel more efficient than the classical kernel. Okay, so they design a label. Okay, in that case, the quantum kernel method is better than the classical kernel method and better than the other benchmark. Okay, but the real thing is that label after the computation really match the original label of the data. Okay, that's something we need to think about. Okay, so this one I guess I already I can talk a little bit more about. So for this approach, because it's a photonic framework, okay, all elements are linear elements. You're using the mirror and they're using the phase shifter. All are linear elements. So in the process, there is no entanglement involved. Okay, so zero entanglement here. And also the dimension is not too high. Okay, we just use a very small circuit. And also if you physically compute the overlap is much faster. Okay, by definition, okay, you for the real quantum computer do quantum machine learning, quantum kernel. Okay, so it's just a cartoon to tell you that we can forget about ideally, okay, forget about the hidden data center, okay, and use this just a photonic method to do the task of the classification. And potentially, I can do something I'm working on is the classification task of some data generated from biology, okay, and for example, this I already mentioned some medical case, okay, can be doable in the near future. Okay. Now I'll talk a little bit more because it's related. I write something before, not on the photon sampling, but spin sampling. Okay, I improve a little bit. Okay, so you know the general picture. Okay, for this kind of textbook example for the algorithm is that you know that it beat the classical computer, but if you really look into how to build up the quantum circuit for this algorithm, you see even for 10-bit number, okay, it's very small number, might be 21, okay, and the binary bit, okay, you need 1 million C log gate, okay, so that's why, okay, IBM can only factorize 15, okay, and they can factorize 21, okay, but not other number, okay, currently, okay, this hopeless, okay, and there's another task, okay, what they have done in 2019, okay, that's the random circuit sample, okay, it's not the strict one, okay, it's a doable one, okay, so historically in the 2019, the 55 qubit, okay, they perform a task, okay, this task, okay, in 200 seconds, okay, and they claim that classical computer will take 10,000 years to do the same task, but after some years, you know, very smart person in the world, okay, so someone using 1,432 GPU, okay, then they do the same task, they do 7 times faster, okay, than the original experiment, and then with further optimization, yeah, because they have many GPUs, they can say they can have a 15 times speed up, okay, so 7 times 50, okay, speed up, okay. So the lesson is that without a theoretical proof, it can be thinkers, okay, so sooner or later it can be quantized, okay. So this is a take-home message, okay. So this is different, okay. If you don't read the papers carefully, you mix things together, okay. If you read the later paper, then you say, we have the theoretical proof. No, it's not theoretical proof. It's the conjecture, okay, math, okay, called the Hartleyan, okay. So it's a conjecture one, okay. It's a much weaker one, okay. It can be quantized, especially when in the low-mode regime. That means that the number of photons almost the same as the number of the mode. Then it is called a low-mode regime. And in that case, okay, it is already known, okay, the classical algorithm can solve it, okay. That's why recently they still do the Gaussian Boson sampling, but in a very high mode regime, okay. Okay, that's a Chinese Zhu Zhao, okay. That is already 219. We have a one network version in the 2025. Okay, but still in this case, okay, it's the Gaussian Boson sampling. It's not theoretical proof. Okay, This is theoretical proof. This is called a Fock state boson sampling. Okay, different. Okay, the input is not coherent state. It's not a discrete state. It's a strict Fock state. Okay, Fock state, single cubic Fock state, a multi-cubic Fock state. Okay, so it's mathematically proof. Okay, but this will be a little bit more precise. Okay, proof in the high mode regime. Okay, the number of mode much larger than the number of photons. In the following slide, I will tell you more quantitatively. Okay, so.
Sorry, but boson sampling is also not technically proved, is it? Like
yes. All the experiments they do are in this. I already this slide tell you why it's not doable because you need a very good single photon source. Okay, currently, but
there are many. I mean, there have been a number of experiments of quantum advantage with boson sampling. No, I'm not saying that.
They're claiming this. So the boson sampling is a very figure work. Okay, they are mixing things together.
No, I mean boson sampling that they are don't wait.
Theoretically, that's true.
No, there are 4 or 5 papers inside of the field. Like the experimental ones. No, but like 5, 6 years. Maybe more, no, there have been. Of course, proof of quantum advantage is a strong word, but like there have been experiments claiming quantum advantage with boson sampling.
So okay, now I catch your meaning. Okay, so they say they can do this, Fock state boson sampling. Okay. Overlook this part. Okay. What I'm telling you is this. Okay, it's a very strict requirement because if your input is not really Fock state, okay, you cannot have Fock state sampling. Okay, that's the problem. Okay, I'm not claiming they're wrong, but need to be look at them, their paper very carefully. Are they really?
Oh, again, you mean like if there is noise, it might be easier.
Yes. And the input is not a very single photon source. Okay.
Yes, that is true. But also, in the ideal case, it's not technically proved with hardness. Like Aronson's results still rely on a few conjectures.
Yes. I will talk about later. Immediately in the next slide. Yes. So. There's something wrong. Okay, so also not proven. Okay, why they can accept that it's not cannot do classically. Okay, but in the case of SOR, it's a million of gate. Okay, so not possible to do. And the Gaussian sampling. Okay, that's the conjecture. And for the Fock state boson sampling is the proven under certain condition. Okay, this is the more latest condition, your number of mole and least scale is the number of photons square. Okay, it's still in the high mode regime, but might be a little bit middle mode regime. Okay, so the linear regime is not provable. It's too difficult. Okay, and in my case, I changed a little bit. It's not a boson with infinite number of energy levels with a certain cutoff. Okay, you have n levels. So in not n, the d levels. Okay, and in that case, it's just a trick. Okay, to change it into a quasi-linear. Okay, I will talk about it later. Okay, then experimentally, this might be easier. In certain cases, okay, each method has disadvantage and advantage. Okay. Here is the idea. So why you need a large number of moles is to avoid this kind of birthday paradox. Okay, so birthday paradox means that we have you have a classroom with many persons. You have large enough of persons because you have only 365 days. So if you have around 50 persons, then you might have over 50% of probability that I and you have the same birthday. So this is called the birthday paradox. Okay, so you need to either increase your number of moles or decrease your number of the photons. Okay, to avoid this birthday paradox means that the two photons in the same mode or the two persons in the same birthday. Okay, so this is called the birthday paradox. But it's a technical one, in the proof of the quantum advantage. And And then because the collision probability is like this, okay, you exponentially scale with this n square over m. Okay, so you need this guy to be as small as you can. Okay, and okay, so now you see why is the n scale as the number of photon square. Yeah, so this you don't want, okay, but if you don't have the strict boson sampling, now I change it into another system, okay, for example, the spin system, okay, then you have the 2s, okay, number of levels, okay. In that case, this is allowable, okay, that's the trick, okay, that's a trick, okay, and then for the spin half is not good, okay. So for the spin half it's even worse, okay. It's the scale of the n4, okay. So it's not good. That's the original paper, but I used to check a little bit, okay. Then for the last spin, okay, theoretically, okay, and then it become a quasi-linear scaling, okay. So m proportional to n 1.25, okay. So it's much better, okay, the scale. But experimentally, it also introduced the difficulty, okay. The high spin is not easy to do. Okay, and well, I just draw something. Okay, that's you already know. Okay. Okay, so for this case, the error bar is okay. So the constant is this. Okay, so you have this kind of m proportional to n1 minus 3 over 2s. Okay, so you see it's inversely proportional to the spin quantum number. Okay, so you have the larger spin. Okay, the scaling is more linear. Okay, and it actually, in principle, it's doable. Okay, in the trap ions and Fourier terms and spin qubit. Okay, but this tape will tell you the truth is that for the trap ion, maximally you can do some sample culture of ions, and you can do the long range. So this is might be the one platform that is doable. Quantum, you have more. You have a few thousand of atoms, but used in the old time is not this worse because they don't have long range. They only have the short range interaction. But now they change it a little bit, okay? And then the so-called neutral atom is more controllable. So with the revealing experimental platform, they can also do the long range. So these two are more doable, but still, you see the maximal S here, and S equal to 3, S equal to 9 over 3, okay, still not equal to 6, okay? And for spin qubit, even worse, okay, they only can do the spin half, okay, and the maximal number of n is 12, okay, so forget about these two, okay, D wave also they are fixed to spin half, okay, so the two can be forget. Okay, yeah, that's just a cartoon, okay, we skip it, okay. And it's just my suggestion is that if that photonic quantum platform, photonic quantum kernel is doable, then using my trick, okay, it can be doable in other platforms. And in that case, you can introduce entanglement into the quantum circuit. Might be helpful, critically helpful in this kind of applications. I don't know, okay, this something has not yet done. Okay, I tell you something has done, okay, something has not yet been done. Okay, that one already in the archive. This one is something that I'm doing, okay, so it's just very conjectural one, okay, the biological application, okay. And the typically you will see something in this, okay, so it's a token, okay. If you're not familiar, you know that each line they have the very token, something like this. You have the carbon atom, then the carbon atom, maybe 1,000 carbon atom, and then on the sides on the side, you have the oxygen atom or the nitrogen atom, okay? You have many, add together, you have 10,000 number of atoms, okay? But this is a bond, okay, a carbon bond of the protein, okay? So it's a very complicated thing because it will flow in the three-dimensional space, okay, and they have very complicated topology, okay? So you need to find some way, okay, to embed in the quantum space, okay, then to learn, okay, which floating is the correct floating, okay, without the knowledge of the real experiment. Okay, this is something people want to know, and if you start everything from the quantum computer using the quantum computer, hopeless, okay, because I already tell you this protein is a very huge guy. You have a few thousands of atoms, so it's hopeless, okay. A more doable way is like this, okay. So you still use the classical training, okay, with all the AlphaFold 3 methods, okay. You whatever method, then you generate many numbers of possible configuration that they call okay, the core. So you have, for example, when you have a 500 core of the same protein, then you can inject it into this method I tell you before, in the photonic quantum kernel method, and you embed it in all the information, okay, the angle or the position of the atom into the green splitter or the phase shifter of your circuit. Then you can do the scoring, okay, you try to, in the very beginning, try to find out which one is more close to the real one. Real one means the experimental structure. If overall your differential is less than 1 times of the 10 to minus 10 meters, then it's good. Okay, if you give it 8 times, then it's bad. Okay, so you want to have a scoring or have a classification of what is good structure and what is bad structure. And this is doable, okay, this is doable, because you don't need to handle the complicated protein folding parts, okay, that's the most complicated part. Okay, you only want to have a scoring of the decoy, okay, and for example, this one is what I'm doing, okay, and you can take others, all the data are publicly, you can download from the website, okay, and if there's a single domain proteins, then you don't need our quantum method because the AlphaFold 3 already can 5%, 98% correctly predict what's the protein folding. Okay, but they fail. They do fail in certain kind of proteins. For example, this protein they have a rigid part, okay, rigid part, but they have some soft part, okay, that means that this does not appear in all the data banks, okay, they don't know, okay, what is the correct angle and correct distance, okay, and for this kind of complicated proteins, they fail, okay, so in that case, the quantum method might help, okay, and this is a more new one, okay? Always more complicated than your form, okay, the biology, okay? For example, this one, this competition online is neither Olympic in the biology, okay? They do it every 2 years, okay? But this year they will do it again, and they will release all the code, the number of the acid of the protein, then you try to predict, okay, that your banks, okay, to predict the correct folding, okay, but that one is still doing, okay. So what I'm using is the last year, okay, this is the 16, okay, of the Olympic, okay, and they have many, okay. You see the T 12 and 1,200 means that there are many atoms, okay. And for example, this atom they have 45 decoy, okay, and each one they have 5 teams, okay, so each team do 5 predictions, and the long, and just give you some impression of the real data is that okay, you have 1,041 atoms, okay, per decoy, and that's something I'm doing, okay, very primary, okay, just give you some impression of what's the real data, and then, for example, the backbone of the plugin, okay, if you only extract the main carbon atom, so you have the 45 carbon atom, then you now we have array of the shape, okay, 142, 139, okay, and 3 means the dimensions, okay, you have the dimensions, 3 dimensions. And then, but in that case, it's not so straightforward because the data is the rotational symmetry. Okay, so if you directly use it, you very bad. So the typical procedure, okay, you do the alignment first, okay, because every decoy, you don't know the center of mass, and 3-dimensional looks different. You need to make a rotation first to align it, and then you can compare. So this is called alignment, and then you compute the distance matrix. Then this is input, okay? But this is still too large, okay? So I'll show you. It's a upper triangular, it's a triangular matrix, okay? Then the dimension is 8,000, okay? It's horrible, okay? I already tell you for the quantum kernel, you cannot have too high dimensions, so you need some reduction, okay? And there can be many reductions. One of them is called the PCA. Then you try to reduce it, okay? Now your input is 20, then dimension is 20, okay? 8,020. And then you do the feature map, okay? And the simple one, I already tell you, okay, if you have your data, okay, you have 20, x1 to x20, okay, then you just pass through it, okay, 20 modes, okay. But I will discuss with Kaviani, okay, maybe that's not enough. So I'm upgrading it, okay, how thinking about the cost talk, okay. But this just gives you some ideas, okay. Then you can compute the square fidelity, and then you compare 2 things, okay, the classical one, the now is the Bolshevik one. And very primary result, okay, I think this is already 2 weeks ago, I have not yet put the label on it, okay, and the feature is there, okay, you see the classical kernel, we map things more here and there, okay, the Bolshevik kernel will more concentrate. But I will report to you later when you really put the official marks on the points. It's not so simple. Okay, somehow you will see might be the number 1, the nearby to the number 100. Okay, so it's not so simple. Okay, the biology is very complicated, so I will skip it. Okay, in principle, one can do the high-level analysis, even the topology analysis, but with the label, it makes things a little bit complicated. It's not purely topological. Okay, so I just show you some possible doable, okay, approach to the really complicated biological data. And hopefully next time I will report something more robust. Okay. Yeah. I think that's the large page, right? Okay.
Okay. Let's begin. Other questions? There have been a lot already. Okay. If not, let's take the again.
Okay. And I can stop.